Right, so the title is a little bit complicated. I realized while preparing the talk that actually what I really want to tell you about is this, the geometrization or a geometrization of two manifolds. But of course, yeah, this title is a little bit my motivation for the talk. So let me change the color. Right. So what I want to talk about is two equivalences. I think they are formulated as bijections, which some of you might know. I'll explain the notions during the talk. So there's one equivalence of symplectically two algebroids with Courant algebroids, which is due to Roytenberg, Roytenberg, and independently Poisson Severa, I think from the around 2000. Namely, symplectically two algebroids as graded geometric formulation of Courant algebroids. But there's also another bijection, which is due to Blanc in his PhD thesis, 2012, of Lie-2 algebroids with VB-Courant algebroids. And if you look at those two lines, you might be slightly puzzled, because if you have a look, I mean, symplectically two algebroids are special Lie-2 algebroids, while VB-Courant algebroids are special Courant algebroids. VB stands for vector bundle. So VB-Courant algebroids are Courant algebroids over vector bundles, which have a linearity property. We see that. So more on one side seems to be less on the other side, which seems strange, but of course it's not. There's a very simple explanation. It's because in this equivalence, Courant algebroids are actually tangent prolongations of Courant algebroids. And then they fit very well as a particular class of VB-Courant algebroids. So I guess that's what I want to explain. And at the basis of that, really the basis of these equivalences is an equivalence of two manifolds with a special type of double vector bundles. So geometrization of two manifolds, which was my subtitle. And so the plan during the talk is to explain first a few definitions. So at least roughly what those objects all are. Then we'll talk about double vector bundles and this geometrization. Here I should note, so double vector bundles are not two vector bundles. Sometimes a priori people think it's similar, same structure. We'll learn tomorrow about from Konrad what two vector bundles are, I think, and I'm looking forward to that, because I think also they are not the same objects. There must be some relations between them. So I hope we'll discuss that. And then, should write here and this, the geometrization, and then at the end I'll give you some applications. I mean, not applications, but I'll explain what happens now when we have this basis equivalence, when we add geometric structures on both sides of our equivalence. Right, so that's the plan. And we begin, as promised, with a couple of definitions. So if you didn't know any of the objects mentioned before, you'll learn a bit about them now. So first of all, positively graded manifold. So an n-graded manifold of degree n, which I'm going to call an n-manifold for simplicity. It's just a smooth manifold, but you enrich the smooth functions by graded generators. So you have a locally free and finitely generated sheaf of n-graded commutative associative unital algebras, which locally look like polynomials in graded generators with coefficients in the smooth functions, local smooth functions on the manifold. And those generators, they graded commute. Right. So the two important things to say here. First of all, first of all, such a graded manifold is always non-canonically split. So you always find an isomorphism to simple objects, which I'm going to explain. So which means that M is isomorphic to a simple graded manifold, which consists of n different vector bundles over the same base M over M. So this notation means that you can just understand M as having sections of E1 stars as generators of degree 1, so those generators, and E2 stars in degree 2 plus products of two elements of degree 1, etc., until degree n. And so that will be important. What will also be important at the beginning of the talk is that if n equals 1, so a 1 manifold, oops, sorry, a 1 manifold is, well, in that case, the splitting, this isomorphism is canonical. So it's always M equals E1, which means that the functions on M are just the sections of the exterior algebra of E with the obvious grading, which I'm going to call omega bullet of E. And this correspondence of one manifold with vector bundles is really easy. If you start with a vector bundle, well, you're just going to construct this. You're just going to take this exterior algebra and you'll have a graded manifold of degree 1. Conversely, if you start, if you just look at the definition and start with a 1 manifold, then you're going to take your generators, your local, you're going to overlap your smooth manifold M with trivializing sets. And on each trivializing set, you'll have generators like here, psi1 to psi R1. And on overlaps of two charts, you're going to write your generators on chart alpha, U alpha, as linear combinations of the generators in the chart U beta. And the coefficients will give you just simple vector bundle cocycles. And you're going to just use them to paste those sets together to a vector bundle. So that's really easy, straightforward, and really bare hands. And what I want to show you is a construction like that in degree 2 as well. Right. But before we do that, let's look at some geometric structures. So on degree 1, one manifold, which means a vector bundle, we can put, well, we try to put a Lie algebroid structure. So a Lie algebroid structure is a vector bundle A over a smooth manifold M, which is equipped with an anchor. So that's a vector bundle homomorphism rho over the identity on M. And that anchor anchors a Lie algebra bracket on the infinite dimensional R vector spaces of sections of A. So you have this Lie algebra, gamma A. Gamma A are the sections of A. While it's not completely wild, you have a compatibility with the derivations along the manifold. That's its Leibniz property. And the examples you should think about, if you look at that definition, if the base manifold is a point, then A is just a vector space, and then you just have a Lie algebra structure. But on the other extreme, in a sense, if A is Tm and rho is the identity, well, you can take the bracket just to be the Lie bracket of vector fields. And then this condition is just the Leibniz condition, and it's very natural. Right, so those are the corner cases, but Lie algebroids, they appear in Poisson geometry. They are very natural there, foliation theory and principal bundles, etc. Right, so if we have that, we consider the one manifold A1, then we equip it with the RAM-like differential operator. So the RAM-like, which means, well, I don't want to write the definition, you can ask me later, but it's just defined like the RAM differential for, in the case where A is Tm, it is the RAM differential. It goes from forms on A to forms on A 1 degree higher, so it has degree 1. And it satisfies some properties, so it's a vector field. It takes a function to a function of degree plus 1. So that's a vector field of degree 1 on our one manifold, and it squares to 0, and dA square is 1/2 of the commutator of dA with itself, because here we are in graded geometry, so we are talking about graded commutator. So we have that, and that's a homological vector field. So a Lie algebroid can be understood as a one manifold equipped with a homological vector field. Right, so a vector field of degree 1 that squares to 0. Conversely, if you start with a yeah, I mean that has nothing to do here. So if you start with a one manifold equipped with a homological vector field, well, you're going to identify your one manifold with sections of E star, and then no, I think I mixed up things. Well, it doesn't matter. In any case, you're going to identify your one manifold with a vector bundle, and then you can write your homological vector field in local coordinates. It's not important now to understand that equation in detail, but when you do that, you work in local coordinates, you will be able to identify an anchor and a bracket on sections of E star, which will define a Lie algebroid structure on sections of E star, because Q square is 0. That will be the Jacobi identity. So we have that, and so we find that the algebroids are equivalent to this pair, so one manifold plus, one manifold plus homological vector field, which are then called Lie-1 algebroids. And then, so that's due to Weintraub, this equivalence, that's now really standard. Partly because of this equivalence, we define then a Lie-n algebroid as an n manifold with a homological vector field. So degree 1 and squaring to 0. Okay, and what we want to understand now is, well, how can we try to do the same construction as in degree 1, where when we are in higher degrees, in particular degree 2 now for the 2. So that's the question. Remember, I said at the beginning that the two algebroids are equivalent to linear Courant algebroids. How does that work? So first of all, a Courant algebroid is now a vector bundle over a manifold. And this vector bundle is equipped with a non-degenerate symmetric bilinear form. Again, a bracket on sections of the vector bundle. This bracket is again R bilinear, but it's not skew symmetric. So it's not a Lie algebroid bracket. It's not a Lie algebra bracket. Well, because it's not skew symmetric, but it satisfies Jacobi identity if you write it in Leibniz form, which means you write the bracket as a derivation of the bracket, and the non-skew symmetry of the bracket is controlled by the pairing, as in this equation. And the pairing itself is compatible with the bracket in the sense that the bracket is a derivation of this pairing. So again, there's not much time for details, but the prototype is a structure on Tm plus T star M as a vector bundle over M with a canonical pairing of Tm T star M with T star M Tm, and a bracket that extends in a natural manner the Lie bracket of vector fields on Tm. And that was defined by, that example was studied first by Alan Weinstein and Courant, and independently also by Irene Dorfman in the late 80s, I think, in the context of Hamiltonian systems with constraints. But then that example really became prominent in the area of generalized complex geometry. So it's a very important example. Right, so that's this side of the equivalence, Courant algebroids. We'll see VB-Courant algebroids a little bit later. And on the other hand, we had Lie-2 algebroids. So Lie-2 algebroids, we had the definition as a special sheaf and a homological vector field. But I said that two manifolds can always be split, non-canonically, but still, when you split the two manifolds, then your homological vector field will boil down to some structures. And these structures you can get by just writing the homological vector field in coordinates. And then, right. And so what you get is, I should say, so for notation reason later, the Q is E1 and B star is E2 in the splitting. Remember, so the two manifold is E1 plus E2 in the splitting. And the Lie-2 algebroid becomes, well, a skew symmetric linear bracket on sections of E1. That's this one, which is not a Lie algebra bracket, but it satisfies, so it has an anchor and it satisfies a Leibniz condition in both entries. So it wants to be a Lie algebroid bracket, just Jacobi is missing. And also the Q wants to be represented on B or on its dual. I mean, it doesn't matter if it's B or its dual. So there's a connection of Q on B, and those two objects are really not integrable. So again, Q is not a Lie algebroid bracket. Q is not a Lie algebroid. B is not a representation of Q, but the Jacobi identity and the Jacobiator, sorry, and the flatness or non-flatness, the curvature of the connection are measured or controlled by a free form on Q with values in B star. So those are all objects that you get from writing down your homological vector field in coordinates. So again, there's really no need to understand all the details. I see maybe this as somehow some additional technicality. What we can remember the structure as is some space that wants to be a Lie algebroid but is not, because Jacobi is not satisfied with a connection which is not flat, and the failure of those two things to be integrable is measured by a form which itself is invariant along the connection. So in a sense, we have a Lie algebroid with flat connection, but up to some homotopy, right? And that's a split Lie-2 algebroid.
So I'm sorry to interrupt a little bit. So these guys, when n is a point, right? So these this bracket is just the Lie. This one is just going to be a Lie-2 algebra.
Yes.
And this bracket is just the Lie-2 bracket, and the connection also the Lie-2 bracket, and the omega is the 3 bracket, isn't it?
Yeah, you can also write it as a bracket on Q plus B or Q plus B star. I don't remember. and that would be the L2 in the B2 bracket. Yeah, you can
realize this differential geometric version.
Yeah, thank you. So a priori, the split V2 algebroids and the Courant algebroids, I mean, there are some brackets, but they are really different types of brackets. So it's not clear at first sight how they fit together. Right. So in order to understand that, we're going to take one step back and forget about these homological vector fields and just look at the two manifolds and geometrize them as some structure. Right, and the structure is going to be a special type of double vector bundle. So what is a double vector bundle? Again, it's not a two vector bundle. It's a commutative square of vector bundles. So we have a subspace D, which has two vector bundle structures over two sides, B and Q. And these two vector bundle structures will, in a sense, commute, in the sense that the two additions are compatible. The prototype, if you're interested in learning that, you should always start with, if you have just a vector bundle E over M, you should take the tangent bundle of E. So obviously, E as a manifold has a tangent bundle, so TE over E is a vector bundle, and E is a vector bundle over M. And over M, we have also the vector bundle Tm. And if you take the tangent prolongation or the tangent functor on all the structure maps of the original vector bundle E over M, you will get a vector bundle structure on TE over Tm, which is really nice to understand how everything works. And over here, you can see easily that if you take a vector in TE that projects under the two projections to the two sides to 0, well, if it's your vector project to 0 in the tangent of L, so it will be tangent to the fibers of E. And the other hand, if it projects to a 0 here, it will be based at a 0 of E. So we're looking at vectors in TE that are tangent to the fibers of E and based at the 0 section. It's easy to see that that's just again a copy of E. So if you take the intersection of the two kernels of the two maps here and here, you're going to get again a vector bundle over E. In that case, it's E, but in general, it's always going to work. So this double kernel, which is called core, is always vector bundle over the double base M. And here also, it's important to know that D is always non-canonically isomorphic to a decomposed double vector bundle, which means D is isomorphic as a double vector bundle to D fiber product over MQ fiber product over MC, which you equip with the projection on B in the first factor, the projection on Q, and fill your diagram. You will have core C, and just to write maybe one vector bundle structure, I write it here. The vector bundle structure of this fiber product as a vector bundle over B is just a pullback on the projection of B of the vector bundle Q plus C. So over B you add in Q plus C, over Q you add in B plus C, and you get a double vector bundle. So right, and here everything works well. So it's also an example that is interesting if you just want to understand what's going on. Okay. So then we're going to equip those double vector bundles with a metric. So the D we're going to call E, again with side B, Q, M, and we're going to put a metric on this vector bundle, so a non-degenerate symmetric pairing. And we're going to ask for this metric to be linear. So I'm not going to define intrinsically what it means to be linear. I just say linear and non-degenerate imply that the core will have to be isomorphic to Q star, and there will exist a decomposition of E as B times Q star, such that the metric is just B Q tau with B, same B, because the metric is in the fibers over B. Q prime tau prime is just a canonical pairing, tau prime on Q plus tau on Q prime. So that's a metric double vector bundle. And while I'm on this slide, let me maybe say, so on a double vector bundle, we have special sections of E over Q or E over B. And if we have a decomposition, it's really easy to express those sections. So if we take B, a section of B, then we'll be able to define B tilde, which is going to be a section of E over Q, which is going to be linear. L stands for linear. By just saying in the decomposition, B tilde at the point QM is the double base point, is B at M, QM, 0 Q star M. So you get a map like this, and it's easy to see in a decomposition that such a linear section is a vector bundle morphism. When you turn your head, it's a vector bundle morphism from Q over M to E over B with base map B. And if you do a similar construction, but this time with a section of Q star, you're going to get another type of special section, which I call core section. It's adding core elements somehow, very simply add the Q's. So you just do the same construction. So each section of a Q star here of the core will give you a special side section of E over Q. And when we look at those sections, so the linear sections, again, I say those B tilde are prototypes of linear sections. We're going to be able to define CE as a space of linear sections of E over Q that have isotropic image. So isotropic in the sense that if you take X at a Q, so Q prime, two elements of Q over the same points in M. So X at Q prime, because the linear section is a vector bundle morphism over a section of B, they will both project to the same B in B. So you will be able to pair them in E over B and you get 0. And we're going to consider the set of those isotropic sections with respect to our metric. Right. Right. So a very quick word on the dual picture, which is important here. When you have a metric double vector bundle, you can dualize it as a vector bundle over Q. And well, if you don't know double vector bundles, you will not know it. That if you dualize a vector bundle, a double vector bundle over one of its sides, you're going to get again a double vector bundle, but the other side and core are dualized and flipped. So we get a new double vector bundle, and the metric in that picture is going to be an involution, which squares to wait, no, let's just write it differently. Which squares to the identity, and which in a no, not one. Sorry. No, I said exactly one, but there exists a decomposition, not just only one. So there exists a decomposition of E over Q as Q times B star, such that I of Q prime beta is Q prime Q beta in the decomposition. So that's the involutive picture, which is equivalent by dualization to the metric double vector bundle picture. Okay, so I claim that those objects are two manifolds. So they are the geometric version of two manifolds. So now I'm going to explain how that works. We go back to metric double vector bundles. No, that's the longest slide, I promise. So the double vector bundles were originally defined by Pradine in the 60s. Pradine was a student of Ellersman. And so he defined them as a total space D with a double vector bundle chart in the same sense as a vector bundle can be defined as a space with a vector bundle chart. So you have a projection to M that will be our double projection this way or this way. And you have local bijections of pi inverse of open sets with the open set U times V1, V2, V2 dual, where V1, V2, V2 dual are vector spaces, such that when you take an overlap of two charts, the change of chart is, well, in the first entry, in the first vector entry, just a cocycle. In the second also. In the third, another one. Sorry, I said so. So Pradine's definition was just for double vector bundles. So here you have a third space, but I'm writing right away for metric double vector bundles. So cocycles, simple cocycles A, B, satisfying usual cocycle conditions, but also a correction term somehow. The idea is really, if you start with your double vector bundle and look at, so local trivializations of the sides and core, using the decomposition, you will have an isomorphism like that. But when you change your local trivialization, a priori you also change the decomposition, and that's really the change of decomposition. It will keep the sides fixed and just add something to the core. In any way, so you get those cocycles, A with values in GLV1, B with values in GLV2, and this omega with values in, I guess, Q-symmetric matrices. Well, B1 star tensors Q-symmetric matrices on V2. And as I said, the A and B satisfy the standard cocycle conditions of a vector bundle, but the omega satisfies a new cocycle condition, the compatibility with the A and B. So when you change two times your chart, the omega gamma beta of X applied to a vector V1, like here, it's omega gamma alpha on A of the vector, A alpha beta, plus a transformation of omega alpha beta on X V1 with a multiplication of this matrix on the two sides by V alpha gamma and its dual. So it's, in a sense, it's a very natural cocycle condition. It's a double vector bundle cocycle condition. So now we are ready. So we take our two manifolds, and we just do, like I said, orally in degree 1, we just do the same construction. We cover the base manifold with trivializing sets for the two manifolds, and we start with the degree 1 generator. So on overlaps of two charts, U beta, U alpha, you're going to write your degree 1 generators as linear combinations of the degree 1 generators on the other chart, and you get nice cocycle. I mean, nothing happens, it's just a vector bundle cocycle. But when you do the same for degree 2, well, the generator of degree 2 on the chart U beta is going to be a linear combination of generators of degree 2 of the chart U alpha, which are, well, not only these guys of degree 2, but also products of guys of degree 1. And when you write this general formula, well, my ith generator of degree 2 for the chart beta is a linear combination of all those degree 2 elements, where you're going to get the B and the omega, and they will satisfy the cocycles, the same cocycles as this double vector bundle. So it's very bare-hand construction. You start with your local generators, you construct the cocycles, and you can place them to a metric double vector bundle. Conversely, so that's the functor going from two manifolds. So that's going from two manifolds to metric double vector bundles. And going back, if you start with a metric double vector bundle, E over B over Q over M, then, well, this algebraization in the sense of E is going to have C infinity E, let's write it like this, as generators of, not CE, this isotropic sections of E over Q as generators of degree 2, sections of Q star, so actually cross sections as generators of degree 1, and of course functions on a double base as generators of degree 0. And then you can go back and forth and you get an equivalence of categories. Okay, so once we have that, we'll add some geometric structures. But before that, let me just mention, I mean, it's still in preparation. There are a couple of little details to be checked. We can do a similar construction for n manifolds, just that for doing that, we have to forget about the metric picture, but look at the involutive picture. So we're proving that n manifolds are equivalent with n-fold vector bundles. So this time we have a total space and it has n different vector bundle structures over n bases, which are themselves n-1 vector bundles over etc. with the last structure, which can be confusing at the beginning. But n-fold vector bundles, the involution is now understood as an S2 action, right? Involution identity is an S2 action. And here we were able to identify an SN action that will make the equivalence with n manifolds work. Okay, so let's move on. Now it's going to be even more sketchy. So once we have our equivalence of two manifolds with metric double vector bundles, well, we can add a structure. So on the two manifold, we add a Poisson bracket. So Poisson bracket on the function that decreases the degree by 2. So Poisson bracket of degree -2. And now that we have the equivalence of M with a metric double vector bundle, which I forgot to mention, really specializes to an equivalence of split two manifolds with decomposed metric double vector bundles. Well, the Poisson structure, you can either check in a splitting, or you can check in the involutive picture, because the Poisson structure will define just the Poisson structure on the involutive double vector bundle. But at the end of the day, you get a Lie-algebroid structure on B, a Lie-algebroid structure on E over Q, such that this whole thing is a VB-algebroid, so compatible with the linear structure, and it's also compatible with the metric, in the sense that if you dualize the VB-algebroid over B with the metric, it's going to be isomorphic to itself. Okay, so that's very quick. Just to say, you add the Poisson bracket. On the other hand, it's really immediate that you get the Lie-algebroid structure. And something similar happens where instead of adding a Poisson bracket, you add a homological vector field. So remember that we had split Lie2 algebroids, so split two manifolds with a homological vector field. That was here, all those structure objects. And now that we have the equivalence of two manifolds with metric double vector bundles. We're going to split the two sides. So split Lie-2 algebroids we understand very well. And when we split a VB-Courant algebroid, we're going to notice that, right, just on those linear and cosections that I identified, but the other side, linear and cosections over B, the Courant algebroid structure is just going to look like the objects of the split Lie-2 algebroid. So the bracket is going to be this bracket on the E1 part. The connection is just going to be the anchor of my linear sections. And this curvature form will be the failure of the bracket on Q to be really the same as the bracket, the Courant algebroid bracket. So then that shows that once you have the correspondence of really the basis, two manifolds and metric double vector bundles, well, the rest is just writing down what structures you have. So you get this equivalence of the category of Lie-2 algebroids with the one of VB-Courant algebroids. And when you mix that, or you combine that with the equivalence of Poisson two manifolds with metric VB algebroids, well, you get an equivalence of Poisson Lie-2 algebroids. So that's a manifold, a two manifold with a Poisson bracket of degree -2, a homological vector field that preserves the Poisson bracket. On the other side, you get E over B. So that's Courant algebroid, Lie algebroid over Q, M, Q star. And Q preserving the Poisson bracket, I must say, in that picture is really difficult to express. So it's a lot of work. But by looking at the compositions, you can really show it's just the same on both sides. You had some structures, a split Lie-2 algebroid that is compatible with a representation of homotopy, which is the same as the Poisson structure. So that works well in a splitting. And now we can ask, okay, so now we're ready. What happens when this Poisson structure is actually symplectic? Well, you can show that when the Poisson structure is symplectic, then the Lie algebroid structure, that one, is just a tangent prolongation of a vector bundle. Sorry, the tangent bundle of a vector bundle, which is a VB algebroid over the Lie algebroid structure on the base, Tm. And the Courant algebroid is just a tangent prolongation of the Courant algebroid structure on E. And then the decompositions or the splittings, which are equivalent, they are just metric TM connections on E that preserve the metric. So now the correspondence is given. I have 1.5 minutes left. I just wanted to give you a little application, little picture where these correspondences are useful to explain what's going on. And the beginning is very easy. So there's the notion of matched pair of representations. So you have A and B, the algebroids over M, and they act on each other. So A has a flat connection on B, B has a flat connection on A, and these two Lie algebroids with their representations on each other build a matched pair if, well, either of two things are satisfied. So first thing, A plus B over M can be equipped with a Lie algebroid structure such that A, B are sub-algebroids, and the bracket of a and a B is minus nabla BA, nabla AB, where nabla are the representations. Or a completely different picture, that would be the by-cross product. Different picture, A times B is a double Lie algebroid with trivial core, so which means that you have, sorry, you have two Lie algebroid structures that, in a sense, that I will explain very quickly, commute. So we have two very different ways of expressing this matched pair condition, which are two different structures on spaces that are actually are spaces the same, but not, I mean, on one side it's a sum of vector bundles, on the other side it's a double vector bundle. And now in the context of the equivalence before, it's easy to understand, because if you have a double Lie algebroid, well, you can show that in a decomposition, there's a double, I mean, there's a compatibility of the two Lie algebroid structures, which is expressed by saying that there's a matched pair of representations up to homotopy. So C0 plus C1. So that's really a last thing for people who know that. So matched pair. And when you take this matched pair as a bi-cross product, you get split Lie2 algebroids. Split Lie2, which is C A plus B TM, and which so you get some structure objects. But on the other hand, when you start with your double vector bundle, double Lie algebroid, there's a condition which says that if you dualize D over A and D over B, then you always get new Lie algebroid structures, which are over C, and you get a Lie bi-algebroid, VB Lie bi-algebroid. And a VB Lie bi-algebroid is the same as a VB-Courant algebroid. So over C star, over A plus B, over M, VB-Courant. And then in the decomposition, it's just the same as the split Lie2 algebroid. And when we look back, so that was a split Lie2 algebroid, and that was just the VB-Courant algebroid when you've understood it in the right way. Okay, and I'm going to stop, but I can tell you later about a similar correspondence in the context of Lie bi-algebroids, where you have a double picture and a bi-cross product picture, which are now with those correspondences just the same. If I've understood it well, that's two objects or two equivalent objects that are interesting in double field theory. So if somebody wants to talk to me about it, I would be grateful. Okay, so thank you for your attention. On the remaining slides, I've put references and some tables of the objects if you're interested.
Very much for your talk. Well, are there some short questions? I guess I just leave the section over here. Yeah.
Quickly.
Yeah.
Yes. First of all, yeah. Well, thank you for your talk. Is that? May I say something?
Sure. Yeah, I didn't recognize the voice. Now with your picture is much better.
Yes. No, I wanted to thank you for your talk. I mean, I think it's nice that these ideas are being developed. And my question is, so do you have any kind of a coordinate or splitting free proof of this equivalence between well, what you call two manifolds and the type of double vector bundles you mentioned? I think metric or involutive. That is a two manifold, the way you define it, that basically consists of a pair of vector bundles and an extension of one by the exterior square of the other.
Yeah.
So that's something that I guess it shows up in that cocycle that you wrote down.
Yeah.
Is there a way to construct directly from this data this double vector bundle?
Yeah. Also, I mean, you can extract it from Lie-Blanc correspondence with of Lie-2 algebroids with VB-Courant algebroids, where you put the so on the Lie-2 algebroids, you just take 0 as the homological vector field, right? So let's write it just here. So Lie-Blanc.
Before anything, Madeleine, could you like not erase your handwriting and send the PDF to the second?
I will give it to you. So Lie-Blanc said that Lie-2 is equivalent to VB-Courant.
Mm-hmm.
So in his picture, when you take the Q of the Lie-2 algebroid to be 0, well, on the VB-Courant, you will get 0 as bracket and 0 as anchor. You just the metric is remaining. So you can use his proof, but I find it really difficult to grasp. So his proof is as follows. You start with the Lie-2 algebroid. You take the cotangent bundle of the Lie-2 algebroid, which is a symplectic Lie-2 algebroid. The symplectic Lie-2 algebroid is a Courant algebroid. And somehow from having taken the cotangent, there's some linearity property that remains. But at the level of really functions, I find it very difficult to understand what are really my functions on the Lie-2 algebroid when you start from a VB-Courant algebroid, or what are the sections of my VB-Courant algebroid, or sorry, of my metric double vector bundle when you just start from a 2 manifold. So there is his proof.
Yeah, I think this is I think there's some reduction going on there, and Marcus, that actually, well, this whole story is like just one step above, repetition of the story of the construction of symplectic Lie algebroid from a Poisson manifold, and then a linear Poisson structure from a Lie algebroid.
Yeah.
So you kind of like to do these in sequence, you end up with this tangent prolongation.
I believe that, but my goal was really to do it bare hands because I like to see what are the functions, what are the sections, and I couldn't see it really in that picture.
Okay. Well, thank you. Yeah, I won't hold you much longer. Thank you.